this, what you're looking for is it consistent or inconsistent? Consistent means that it has a solution. Graphically, what does it mean if they have a solution?
That they cross each other.
That they cross each other. Now, I don't see them crossing each other here.
Oh, they eventually
but
do.
Eventually they will, right? The only way they wouldn't cross each other is if they were parallel.
Parallel.
So, even though it's not shown here, they will cross each other. So that would make it, what's your answer here? Consistent.
And independent.
Yeah, consistent, because there will be a solution, there is a solution, and independent because the graphs represent different lines. It's not one line right on top of each other. So I like that one. It asks you to think a little bit, so that's a good thing. Not that it's going to be part of a quiz type question, but you know, if you were to solve this problem with the addition method, they call it the elimination method. Just not really happy with that term. But one way you could do it to get rid of the x's would be this one, to multiply the first equation by 4. Now in doing that, you're going to have a coefficient of 36 here, so you'd end up with 36x minus 16y equals 32. And then multiply the bottom equation by negative 9, so that'd be negative 36x plus 63y equals negative 45. And the nice thing, when you add those together, those drop out. Oops, a little bit below that, so nice. You should be able to solve a system of equations in a lot of different ways. One of them is just graphing. And, you know, I'm not sure I'm averse to putting this one on test. You know, it's just kind of a different form that I would put on than what I've usually put on. But let's take a look at, let me shut this off for the moment. Y equals negative 0.95x, 5x plus 4, and y equals 8.95x minus, I need an x in here, x minus 14.9. So I could ask you a lot of questions about this. I could ask you, is this consistent or inconsistent? The answer there would be consistent. Dependent or independent? Obviously this one's independent, 2 different lines. And then I could ask you a solution. Round it to the nearest hundredth. So you click on decimals there, bam, you've got it. You could also do that in the graphing calculator. It's just not as convenient. There you go. Round it to the nearest hundredth. Beautiful. Let's keep going. Lots of different things can happen when you look at a system of equations. In particular, you could look at something like this. And I think that takes me to our next question on the quiz. So let's do that. Next question. So this system of equations, is it consistent or inconsistent, dependent or independent? What is it? All right. Let's take a look at something here before we do the big reveal. If you multiplied the given system of equations, if you multiplied this right here, the bottom one, by -4, that gives you something like this. And when I add those equations together, then I get 0x, which I'll leave off, and 0y, which I'll leave off. Well, I can't leave off everything. I'll just write 0 equals negative 10. And that's not true. So that's telling you you've got an inconsistent system of equations. Essentially, the lines here, if you graph them, would be parallel. That's what's going on with that one. Now, if you ended up with something like up here, if you ended up with something that was true, if you play around with this system of equations, you'll end up with 0 equals 0. And even though that's silly, it is true. And that's telling you you've got a dependent system of equations. So if all the variables drop out and you get something which is true, that's dependent. If you get something which is false and all the variables drop out, that's inconsistent. All right. You should expect to solve a 3x3 system of equations on the exam. So let's take a look at this one. Now I included this one because I had the fractions, but that's because I wanted to remind you that, look, if you've got something that looks messy and has fractions or something like that, you don't have to work with them. Might be a good idea just to get rid of them. So I could multiply, for instance, this top equation by 3 and get 3x plus y plus 3z equals 39. And that's a little friendlier to work with. I don't have those fractions. I could do likewise with the next equation. This time, what would be the lowest common denominator that I would choose to multiply by here?
6.
6. Perfect. So half of 6 is 3. So that's going to be 3x minus 6y plus 2z equals negative 12. And so on. The last equation, again, I'd multiply by 6. And thank you for giving me the 6 the last time. 6 this time gives me 6x plus 3y minus 2z equals 12. Now that you've cleaned this up, I'd probably choose the top equation and multiply by 6 to get rid of the y here, and multiply by negative 3 to get rid of the y here. That'll give you 2 equations and 2 unknowns. You'll be able to solve for x and z. Once you solve for x and z, go back and solve for y in one of these original equations. Doesn't matter which. Comments or questions on that? You should end up with x, y, z as shown. 2, 6, and 9.
Does it matter what, which order of equations? Will we always still get the same answer? Because my first instinct was just to multiply the top equation by negative 1. So that I can cancel out the, oh, you know what? That's 3x plus y. Is that 3x?
Yeah, it's 3. Yeah, you could multiply. Yeah, that's a different way to do it, and actually it works out good. If you multiply the top equation by negative 1, that could get rid of the x's here, and multiply by negative 2 to get rid of the x's here.
Yeah.
Yeah, that would work out wonderful.
Okay.
So good on you. But expect to solve a 3x3 system of equations. I might, if I did something like this, I'd probably give it to you in 2 parts. I'd say part 1, clean up this system of equations and make it easier to solve. And all I was expected this. And then as a separate problem, I give you a different system of equations and just say solve it. Okay. Let's see here. Now you should expect a couple problems like this. And what I would do for problems like this is not so much make you solve them all the way through, but ask you to set them up. So here's one I'll let you look at home. Here's one we can look at it now. And in fact, let's look at it over here. Exam 4 review. Right here. So what I want to do is I want to remind you how to set up that equation. So it says 1 ounce of each of the 3 foods has the vitamin and mineral content shown in the table. How many ounces of each must be used to provide exactly 24 milligrams of niacin, 14 of zinc, 22 of vitamin C. So at least this problem has gotten nutritionally a little bit better over the year. They used to ask you to come up with different amounts of food to get fat, protein, and carbohydrates, but they wanted you to come up with twice as much fat as they did protein and carbohydrates, which was really backwards. But in any case, your mission, should you choose to accept it, is to set up an equation associated with the vitamin niacin, which is one of your B vitamins. I can't remember if it's B6 or B12. It's one of them. So keep in mind you have this information up here, and food A, B, and C have these nutritional values. So what equation would you set up in association with niacin?
Wouldn't you do?
Wait, don't say it out, because this is going to be a quiz problem.
Okay.
I appreciate it though. So, all right. I'll let you take one more look back at the problem. Get your guesses ready. And all right, let's go.
Can you go back to the equation? Isn't it? Oh. Got it.
Boom. All right. I think I know what that means. Okay. All right, a little change in the leaderboard there. Let's see what the answers are. So what you're going to do with this one is come up with an equation like this. We want a total of 14 milligrams of niacin. So that's going to come from 1 times A, or just A, plus 2 times B, plus 2 times C equals 14. That should be your equation. In a similar way, you can come up with
It's
equations.
supposed to be 24.
Yeah, 24 of niacin.
24, yeah, thank you. 24, 14, and 22. I hope I got did I get the answer right though? Yeah, okay.
Yes, you did.
All right, 24. All right, good. The other equations would be A plus B plus C equals 14, and then 2A plus B plus 2C equals 22. Yay! All right. What else? We did some work with augmented matrices and systems of equations. So writing the augmented matrix, that's just this stuff right here. That's, that's all there is to it. Now, it's in this form that you can start putting things in a calculator and such like that. And that leads me to my next question. Your next question for the quiz. What are the dimensions of this matrix? So, what's its size? So, if you were to enter this in your graphic calculator, how would you do that? What size would you put in there? So, let's go back to our little quiz thing here and move on to the next question. All right, a lot of early guesses on this one. That's good. All right, seems that you probably got your guesses in before time expired, so that's good. All right. Wow, a lot of movement on that leaderboard. All right. So 3 by 4, it's always rows by columns. So it has 3 rows and 4 columns. Does anyone remember what well, I think I joked about this a little bit. My corporate sponsor, remember it was a soft drink? RC Cola, yeah, because it's row and then column. Which, when you're dealing with matrices, everything is in terms of row and then column. It's just the way we roll. All right. Let's go down to this one here. This is a 4x4, but you know, we did stuff kind of like this with 3x3s, and it really just isn't going to matter if you do a 4x4 or a 3x3. We're going to solve this with a system of equations that we're going to put in our calculator. Now, this is different than an augmented matrix. Augmented matrix is simply, we took everything and shoved it in one matrix and put a little line down here. That's an augmented matrix. If I want to solve it with a matrix system, then it's going to look a little different. You're going to have matrix A, which is going to be all the coefficients. And then matrix B is going to be the right-hand side. So the coefficients here are going to be 1, 1, 1, 1, 1, 1, 1, negative 1, 1, and 1, 1, 1, negative 1, 1, 1, 1, 1, negative 1. That's your matrix A. Matrix B is going to be this right-hand side, 3, 1, 1, 3. And to solve that, your solution, call it vector x, is going to be A inverse B. You do this all in your calculator. But if I ask you for a matrix system, this is what I'm looking for. There's going to be two parts. There's going to be this part right here, matrix B, right there. That's just going to be your matrix of coefficients, or of the right-hand side. The other part is going to be the coefficients of this. So that's your matrix A. Now, I'll put those in real quick and show you how to use your graphic calculator to solve that using an inverse matrix. So let me clear this. You're going to hit the second key, then the matrix key, and then go over to edit. And we want a 4x4 matrix. That's going to be matrix A. And I'm just going to type in the coefficients here. 1, 1, 1, 1, 1, negative 1, 1, 1, 1, 1, another negative 1, 1, and then 1's across the bottom, except the last one's going to be a negative 1. So a little bit of a pain there, but you know, not too bad. When you're done, hit the second key, then the mode key to exit out of there. You want to quit that. Now we got to enter matrix B. So try and follow along with matrix B. You hit the second key, then the X inverse key. Again, you want to go over to edit, and then either hit the down arrow and press enter, or just type the number 2. We want a 4x1 matrix, 4 rows, 1 column. And that's going to be 3, 1, 1, 3. That's our matrix. Once again, hit the second key and then the mode key to quit. All we need is our solution, and our solution comes from A inverse times B. So, all right, A inverse times B. Let's see if we can't do that on our graphing calculator. That's going to be the inverse of matrix A times matrix B. So first I got to go get matrix A. I cleared out my key history. You can kind of follow along. Second, matrix, enter, and then hit the X inverse key, second matrix, and then type the number 2, that's A inverse times B. And bam, there's your solution. 1, 1, 1, 0. Now if that went a little fast, I understand. There's a QR code in your notes, and that takes you to a little video that I did on solving systems equations with an inverse matrix. So you can get some more review just by following that link. Yay. All right. It's handy that we just worked with matrices because you will be given a determinant to work with. Now, I'll show you how to work this by hand first, because I am going to ask that you show your work, but I have no problem with you checking yourself on a graphing calculator, and we'll do that next. So, you're going to go across the top row. Remember, there's a little pattern here: plus, minus, plus. So plus, minus, plus. Plus 9, minus 8, plus 5. If that was a negative 8, I'd have a double negative there. So just be careful. But one at a time, you're going to cross off the corresponding row and column. So if I cross off the top row and the first column, then I'll be left with these 4 numbers: 6, 2, 5, and 6. Let's go over to 8. Cross off the top row in the middle column. Can you anticipate me what's going to be left here? 1, 2.
1, 2, 8, 6.
8, 6. Yeah, a couple voices there. Thank you so much. And try and do the last one for yourself as well.
1, 6, 8, 5.
Yeah, 1, 6, 8, 5. Now, I'm going to kind of work up here. It's always a product going down, which is 36, minus a product going up, which is 10. Minus 8 times the product going down is 6, minus the product going up is 16. And one more time, 5 times the product going down, minus the product going up. So 5 minus 48. And then it's just a matter of cleaning things up. 9 times 26 minus 8 times negative 10 plus 5 times negative 43. Woohoo! Wow. All right. When you're ready, let's take a look at the next problem, which is to type in the final answer on this one. And I hope I got this one right. Let me just, So next question. Five seconds. All right. Gabrielle, stretching out that lead there. Okay. So to finish this up, let's see. All we really need to do is multiply 9 times 26, gave me 234. Plus 80 minus 215, that equals 99. That's all there was to it. You can do this on the graphing calculator to check yourself. I have no problem with you doing that. Should I demonstrate that real quick? It's up to you. All right, no takers. So you can do that on the graphing calculator. Here's one that's pretty much a guarantee. It goes along with Cramers Rule. And Cramers Rule was for solving systems of equations. This is exactly the kind of problem that you would get from me regarding Cramers rules for a 3x3 determinant. If you did Cramers rule for the full problem, you'd have to calculate 4 3x3 determinants. That's a royal pain. I'm going to limit it to 1. How am I going to do that? I'm going to give you a couple of these values. D, dx, dz, and I'll give you 3 out of the 4. But for the current problem, I want you to look at this system of equations and calculate dx. What are you going to take the determinant of to get dx? So, all right, well, I know it has to deal with the coefficients somehow. And you got to replace this or do that. So I'll give you a little reminder here. The way you get D is you take the determinant of all these coefficients on the left-hand side. So it would be -2, 0, and 1, 1, 2, -1, 3, 5, and 2. And if you did this determinant, you'd end up with -19. But your goal is to find dx. Remember, we had to do a little something to get dx. So what are you going to do with those equations to get dx? And let me let you take a look at it here. Maybe a little bit clearer. What are you going to do to get dx? Let's just do it. Three seconds. Boom. All right. Let's take a look back at here. And the trick is, you're going to replace, to get dx, you're going to replace that column with the right-hand side. So it's going to be 2, 9, and 22. The rest of this stays the same. So the rest of that is going to be 0, 1, 2, -1, and 5, and 2. But to get dx, you're just going to replace that one column. To get dy, you'd replace the middle column, which is what I did up here. To get dz, you'd replace that column by the 2, 9, and 22. So that's Cramers rule. This is like a 6-point problem. In fact, you can see how I graded it. 2 points for this, 2 points for getting the determinant, 2 points for the final answer. So lots of partial credit. Get as much of this as you can. I'm telegraphing this stuff to you, telling you exactly what I'm looking for. Problem, or section 13.1, start dealing with conic sections. Here's the equation of a circle. You should be able to tell me what the center and radius is. So the center, you look at what makes the squared term equal to 0. The center would be at what? It'd be at 4 and -3. How about the radius? What's the radius of this circle?
5.
Yeah, square root of the right-hand side is 5. So, perfect. And you can see that here. If you go out 5 here to the right, it'd be at the point 9 and -3. So that's on the circle. Beautiful. How about we do a reverse engineer one? In a moment, I'm going to show you a graph of an ellipse, but let me show you the graph of this ellipse and remind you of a few things. So first of all, this distance here, the distance to the right of the center, that distance is 3. So if you have x squared over a squared plus y squared over b squared equals 1, I just found out that a was equal to 3. And in the other direction, going due north, then I end up with b. That's the number underneath the y, so it's going to be b equal 5. And when you put those numbers down here or here, 3 squared and 5 squared give you this respectively. With that in mind, see if you can't reverse engineer the graph that I have on Desmos here. So let me get back over to here to Desmos. I'll shut these two off, turn this one on. There's your graph. See if you can't reverse engineer that one to find its equation. And just to help you out here, that's a 2 there and 0, 5 there. All right. Get your thoughts down. In a moment, I'm going to advance to the next quiz question. And let's see here. Here we go. All right, next question. One last look. Oops. That's not the last look I wanted. There you go. Last look. And over to the next question. Ten seconds. All right. Let's take a look back at our graph. And Gavin, reaching up there into second. Gabrielle still holding on to first place pretty solidly. So you moved a distance of 2 to the right, and then up 5, so it should be x squared over 2 squared plus y squared over 5 squared equals 1. You could also write x squared over 4 plus y squared over 25, but either way.
I don't know why, but the questions, like the options that they gave us was like x squared over 3 squared plus y squared over 5 squared.
Oh, really? I might have screwed up. I mean, I really had to crank these things out in a short amount of time, so it probably was an error. I'll write myself check for error. All right, so I'll write myself a little note. Let's keep going. This one I'm not going to take the time to solve, but basically you plug in a 2 here, and you get 2 squared over 16 plus y squared over 4 equals 1. That's really 1/4. Multiply both sides by 4 to get rid of the denominators. You'll end up with 1 plus y squared equals 4. When you solve for y, you get the square root of 3. You should be able to recognize this as a parabola. What's the big tip-off? That this is a parabola.
There's only one squared.
Bingo. There's only one squared term. Here, you have 2 squared terms. They're both positive, but the coefficients or the denominators are different, so that's going to be an ellipse. Here, the coefficients of the x squared terms are the same. A 1 here and a 1 here, so that has to be a circle. They're both positive and the coefficients match. Here's an example where the coefficients of the squared terms are different. If you squared this one out, it'd be 4 times x squared minus 10x plus 25 plus 7 times y squared plus 6y plus 9. if you squared it out, the coefficient of the squared term here is 4, the coefficient of the squared term here is 7. Well, it can't be a circle because you got two squared terms, it can't be a parabola, it has to be an ellipse. Here's one, you're asked to graph this equation. You should first start by finding the center, and then realize that that's a 5 squared and that's a 3 squared. In the x direction, I'm going to move a distance of 5. So I'm going to start out the center and move 5 to the right. And that's going to put me at the point 9 and 1. If I move 5 to the left, that's going to put me at the point -1 and 1. How far do I have to move in the y direction? 3. So up 3 and down 3. That's going to put me at the point, well, let's see, I'm adding 3 to the y coordinate, so the x coordinate stays the same. 4, 4, and then down 3 here would be 4 and -2. And that's it. That's all there is to graphing that one. We did have some hyperbolas. Gave you a nice graph of hyperbola. How do I know that this is a hyperbola as opposed to an ellipse or a circle?
You're subtracting.
Yeah, you're subtracting. Don't mess this up. My son used to like to call this an epic fail. Right? If you graph an ellipse as opposed to a hyperbola or vice versa, that's really bad. All right? There's just no way I can give you partial credit when you're drawing an ellipse, and I'm supposed to see this rectangle and these asymptotes, etc. It's just not going to happen. So you start out by finding the center. The center is at -1 and 5. You pretend it's an ellipse for just a moment. You're going to go down 3, excuse me, to the left 3 and to the right by 3 to find these points, and then down 5 and up 5 to find these points. Down 4 and up 4. Pardon me, because that's 4 squared. Sorry, I was looking at that maybe. That gives you these. You draw this box, and once you draw that box, then you draw the diagonals. So that's going to be these things right through it. Now, when you draw your diagonals, if your diagonals don't really go right through the center, take a look and maybe make sure that you didn't draw this too high or too wide in one direction, but it should go straight through what you think is your center. Last but not least, draw a nice graph. That's a nice graph. And what I'm looking for is a couple things. I'm looking for a graph that just touches this box once and comes close to but doesn't really touch the asymptote. Now, sometimes I get people doing kind of crazy things here, in part because I think they're worried about touching the asymptote. So when they graph it, their graph, they curve away. They're like, ooh, I don't want to touch the asymptote. No, that's not really the purpose of the asymptote. The other thing I see people doing is they go all the way to the center to draw their hyperbola. Again, that's wrong. So this is a good 7-point problem. That's going to be a point for the center, a couple points for the box, another point, do you open in the correct direction, left and right, because the x squared term is positive. If the y squared was positive, then it would open up and down. So lots of little parts there. Get as much partial credit as possible. Let's see. This one, I left it for you to reverse engineer. Hopefully this is something you can do because you've got the size of that box, so you can tell what the center is. And this has to be, which term is going to have to be positive here? The x squared term or the y squared term? the y squared term because it opens up and down. So that's all your choices. They have a y squared term that's positive. There's the correct center with the correct dimensions for the box. For this one, before you graph it, you would probably do well to divide everything by 36. So 36 here, 36 over 36, and then do x squared. That's a 4, but I'll write it as 2 squared, y squared over 9, which I'll write as 3 squared equals 1. You're in better shape. This one opens left and right. Perhaps one of the most important things here for problems like this one is to realize how many solutions there are. Because a lot of times people will only give me one solution or two solutions. How many solutions are there for a problem like this? There's 4. So make sure you give me 4. Now, you can use Desmos on the exam, and even though Desmos might not tell you the exact answers, sometimes it'll at least let you know how many answers to expect. So let's see, that was a 5. Let's shut that off. Equals 14. And what was the other equation? X squared plus y, or x squared minus 3y squared equals 6. And if you're not really comfortable doing a squared from the keyboard, you can do squared from the palette there. Yeah. Oh, it's a 6 here. Thank you. All right. Actually, let's keep it as a 5 for a second, because I'm guessing that the 5 is not going to give me a nice, perfect answer. But it'll allow you to check your answer, because maybe you'll end up with the square root of 6 or something like that, and you can compare the numerical answer. All right. Now, sometimes you might get nice exact answers. Do you think that that's enough for me, that I'm okay with you just doing a Desmos thing? Probably not. You're probably going to have to solve and show me the work here. But that's okay. One last thing on the problems like this. I'm not a real big fan of people doing plus or minus 3, plus or minus 1. There's 4 solutions. Write them all out. You might not get full credit like that, because my experience has shown that a lot of people don't really realize that when they write that, they mean 4 possibilities like this. So Desmos is great for checking something like this, because you can see, oh yeah, mine intersects at some number that looks close to negative square root of 5, but it won't give you the square root of 5. It will tell you that there's 2 solutions. So keep an eye out for that. And then I guess just a little bit more on section 13.1. This must have got out of order. This is a parabola, but it faces sideways. You can graph this by plotting points, but it's a different way. You're going to plug in values for x, or plug in values for y, and get values for x. Stuff like this. So, and by that, you can plot points. You can also double check it on Desmos too. I have no problem. If I gave you something like this, I'd probably want to see you graph it. All right. I've run over time. Did you want to do the last quizzes one, or should we just go? All right. I see people picking up their phones, so I think there's one last quizzes ones here. This is for circles. 5 seconds. All right, sweet. Let's see the final tally here. Whoa, Kevin! Oh, wow. Hey, excellent on that one. 9 of you got that one right. That's awesome. I'm really, really happy with that. So a little extra credit to everybody today. I will put that in the notes and maybe a couple extra bonus points for our top couple finishers there. So, all right. Have yourself a great weekend. Do take time to look at the handout that I gave you, and see ya Monday.
Thanks again for the quiz.